Hi, my name is Sener Ozonder. In this tutorial, I'm going to talk about physics-inspired models in artificial intelligence. So this tutorial is intended for both physicists and machine learning people. So I'm going to try to explain machine learning in physics language. So in physics, there are models of magnetism, there are ideas of renormalization group, or concepts like partition function. And also, I'm going to go into the details of physics foundations of machine learning. So I'm going to talk about entropy, KL divergence, restricted Boltzmann machines, and more. So analogies and cross-pollination between the two disciplines, I think, will be useful in the future. So concepts used in physics may serve to the AI community to develop better AI models or architectures, and also efficient training methods. So how can physics help? I think it's important to draw connections between physics and machine learning and exploit them. So, for example, in the following slides, I will talk about statistical mechanics and how they are related to the unsupervised machine learning models, restricted Boltzmann machines. So this architecture is actually RBM. There is this hidden layer and there's this visible layer. So we will go into details later. So let's continue. So one question that I can raise at this point is, can we find dualities between deep neural networks and easy physics problems to reduce the cost of training? So the cost of training today, it's on the order of millions of dollars. Can we reduce this by using physics, for example? So the idea of dualities is like this. So let's say you have a strongly coupled 4D quantum field theory. So quantum field theories are, they model the subatomic particles, it's used in particle physics. 4D, what I mean is it's basically 3 dimensions, 3 space dimensions, and 1 time dimension. So because these models are usually strongly coupled, it's really hard to solve them. So what physicists do is they map the problem to another problem, which is weakly coupled. Weakly coupled means it's solvable, but that model is a gravity theory in 5 dimensions. So solve this theory, solve the problem here, and then the idea is just map the solution back. So the question that I ask here, can we find such dualities between neural networks and easy physics problems that we can solve? So all of physics is actually about minimization or maximization of some objective function. So for example, let's start with classical physics. What we call in classical physics is the objective function is basically the Lagrangian. It's kinetic energy minus potential energy. When you minimize the Lagrangian, it gives you the equation of motion for the particle or the wave. For example, if you have, let's say, some glass or some other material with some refractive index, which is different than that of air. So the question is, what will be the path of the light that it goes when it goes through that material? That is actually the minimization. So the nature is using some minimization techniques to find this path. It's basically the minimizing the Lagrangian here. So what do we minimize in thermodynamics? Well, it is the free energy. So in thermodynamics, free energy is when it's minimum, that means the system is in thermal equilibrium. You can think of a gas in a room. So there's going to be some energy term. And so basically, you try to minimize the energy And if you think about with the negative sign, you try to maximize the entropy. So the minimum energy, so there is a trade-off between them. So the thermal equilibrium point is the point where not these ones are individually minimized or maximized, but this free energy is minimized. Now, what about Gibbs entropy? Again, you can minimize Gibbs entropy. The objective function, so Gibbs entropy is this first term. Again, we have some objective function here. So when you try to minimize it, again, this could be for a distribution of a gas in a room. So you can try to minimize this. These are probabilities of the particles in certain states. They can be quantum states or any discrete states. So when you minimize this with the constraint that all the probabilities should sum up to 1, you find the probability distribution for that thermodynamic system. Well, this is more like statistical mechanics. And this Gibbs entropy is actually related to KL divergence, which is used in machine learning as a loss function. Okay, what about quantum mechanics? Same thing. We have the energy minimization in many-body quantum mechanics problems. Let's say you have a benzene ring. There are 6 carbon atoms and 6 hydrogen atoms. So you want to find the electron distribution on this molecule. So what you would do is typically you would use some sort of density functional theory, which where you try to find the distribution of electrons or the wave function squared that would minimize the energy. So whichever distribution minimizes the energy, that distribution gives you the electron distribution on the molecule. So, and we know that the minimization of a loss function or objective function is also central in the machine learning. That's why I mentioned this. So this is one common ground between physics and machine learning. Okay, the next question that I'm going to ask is, can we reach physics explainable AI? So most of the AI models, they are black boxes. They work well, but we don't know exactly how they work. So can physics help in this problem? So, well, explainability is the job of physicists, actually. If I give the example of quantum mechanics, so back in the days, more than 100 years ago, there was this data that when they looked at the absorption spectrum of a hydrogen gas, they figured out that there are certain wavelengths where the gas absorbed the light. So that was the data. There was no quantum mechanics back then. And classical physics, the only thing that physicists knew that classical physics was not able to explain this. So then came Bohr. He proposed a model where he said, there are probably orbit-like regions where the electrons can be, and they can move between these special places, but not in between. They cannot be in between. So when they move, the light, the energy indifference would correspond to the absorbed or emitted light. So that explains the data to a certain level. So that's an explanation. But now we know that this is not completely correct because it doesn't explain certain fine details of the data. And then, so then came the Schrödinger, and he wrote the famous Schrödinger equation. He treated electrons as light waves. That was a revolutionary idea back in the time. So instead of thinking electrons as point particles, now the electrons are waves. They're sort of like clouds around the nucleus. So, and Schrödinger equation can explain all the states and all the fine details of the data. So this is the this is how physicists explain the data. So the question here is, can physics help machine learning? in this regard in terms of explainability. So one of the problems of machine learning is the models are highly susceptible to the noise. So if you feed the input picture, like this one, with some noise, it's, the noise is almost like 7%, it's pretty low. And when you feed the machine with the input plus noise, then the prediction becomes irrelevant. It's a wrong, the model makes a wrong prediction. Same thing happens with the audio recordings. If the audio recording is "How are you?" and if there's even 1% noise, then the prediction becomes "Open the door." So that's the robustness problem of the machine learning models. And another example here is that the model can predict the person on the left as a person, but for the person on the right, it cannot predict it as a person. The reason is that there is this picture on the person, so that picture basically confuses the model, so there's really no prediction here. So machine learning models are highly susceptible to even small noise. So let's go back to physics. So how do physicists deal with the situation where there is noise? Or is there any physical model or situation where the noise does not really change the prediction or the results? There is actually. The subject is topology came to mind at this point. The question here I ask, can topology help solve the robustness problem in machine learning? So Physics Nobel Prize in 2016 went to topology, the application of topology in condensed matter systems. So the idea of topology is simple. So the topological features are robust to continuous deformations. So the idea here is the topology of, let's say, a sphere is characterized by this number, genus 0. You can deform a sphere without making holes. That's the rule. You should not make any holes. Also, you should not destroy any holes. So you have to preserve the holes. So this figure, this sphere doesn't have any holes. So you can continuously, that's the key here, continuous deformation. You can continuously deform it to a spoon, for example. You cannot continuously deform it to a torus or a bagel shape because you have to make a hole, which is not allowed. Okay, if you look at the torus now, there's one hole. So the topological number is 1. You can continuously deform it to a mug because there's only one hole in the mug, right? Okay, if you look at now this figure, it has 2 holes. You can continuously deform it to this teapot because it has one hole here, the other hole is here. So the nice thing about topology is you can, they are robust against continuous deformations. So how do we mathematically express this? Well, for example, in quantum Hall effect, if you have, so it's basically you have some magnetic field and there is some material where you measure the conductivity under the effect of magnetic field. So you can measure the conductivity. It turns out if you calculate it by using quantum mechanics, so this term is just electron charge. This term is just Planck constant. So this part is just constant number, some number. And there is this integral over certain function, and that function is actually functional of, it's a function of wave functions of the electrons in the conductive material. Okay, so the interesting thing here is when you do this calculation or with this prefactor, this calculation always gives you some integer. Okay, so it's either 0, it's either 1 or 2, so it never becomes, for example, 1.3. So this is the nice thing about the topology. So can we find architectures or methods in machine learning that would be robust against the noise? It could be adversarial noise in as the noise added, or it could be the noise in the original data. So can we go beyond the local pixel-based filter convolutions to global topological features so that we can distinguish Chihuahua from a muffin? Okay, so in the following slides, we're going to draw connections between physics, particularly condensed matter systems, and machine learning models. So I will first start with the physical part. So I will explain the physics models, and then move to machine learning algorithms or architectures. So certain materials are naturally magnetic. The reason that they're magnetic is each atom, they're like, you can think of they have spins. Spins are like actually just magnets. So say north, south. So each spin you can think of as a magnet. So each atom has a spin. Some of them are up, down. So they can be in many directions. Well, in this model, we're just going to assume that they're either up or down. The other thing is they can interact with the neighbors. So for example, this one interacts with this one, that one, the one in the below, and the one in the top. So that's the reason why some materials are magnetic, because they are, when the spins are aligned in the same direction, a lot of spins are aligned in the same direction. It's like aligning a lot of small magnets in the same direction, so that creates a global macroscopic magnetism effect. So of course that happens below certain temperature. That temperature could be 500 degrees or 5 degrees, it depends on the material. Below that critical temperature, the material is magnetic. Above that critical temperature, the material loses that magnetic property. So critical temperature TC is important here. So there's going to be, so what happens at TC is called phase transition in physics. It's like the phase transition of water from solid to liquid. You can think of that way. But here, it's not really the solid liquid phases. It's basically magnetic and non-magnetic phase transitions. Okay, so I said these spins, neighboring spins, they interact with each other. So the spin-spin interaction energy favors spin alignment. So the interaction energy wants all the spins or the neighboring spins in the same direction, either up, up, or down, down. So that's what the energy wants. You can think of energy as the force also. If they're not aligned like this, up, down, the force between them, which comes from quantum mechanical and electromagnetic interactions, so the force would try to flip one of the spins so that they are in the same direction. But energy is not the player here. There's also heat. So the heat, so of course, if you have a rock like this, magnetic or not, there is air around, so there is ambient temperature, there's heat, unless you're at 0 degrees, which is negative 273 Kelvin, which is not possible. So there's always some heat, some particle, they basically hit to these spins, and then they try to randomize them. So the heat actually randomizes the spin directions, and that's what we call entropy in physics. And we're going to tie this entropy to the loss functions used in machine learning and also information entropy. Okay, so what is the formula for energy? If you take two spins, okay, the energy is basically negative spin 1 and spin 2. Okay, let's look at this situation. So if you have one spin up, one spin down, basically, if you want to calculate the energy, it's negative. So one spin is up, it's plus. One spin is down, it's negative. So negative plus negative, it makes positive. So the energy is +1. It's high energy. But if the spins are aligned, in this case, you would get positive, positive, and negative. So this would give you negative. This one also would give you negative. So negative, negative, and there's an extra negative here. So that will also make negative. So if they're aligned, what you get is -1 for the energy. So this is the low energy case. So in nature, things try to go to low energy. So that's why spin alignment, as I mentioned before, is favored in this model. So as we cool down, it goes from the high energy states to the low energy states. Of course, I just calculated for 2 spins, but you have to calculate it for all of the spins so that you can find the total energy. So for the total energy, there's going to be a sum here. Okay, so what happens at 0 temperature, let's start with the 0 temperature. So at 0 temperature, there's no ambient heat, right? Because at 0 temperature, that means even if there are gas particles in the system that will create heat in normal conditions, but at 0 temperature, they are actually frozen. So they're not going to hit the spins. They're not going to try to randomize them because it's 0 temperature. So in that case, the only player is the energy. And what does the energy want? So it wants all the spins in the same direction, either all up or all down. So in this case, I just draw the case where all the spins are up. And you calculate the average. So +1, +1, +1. So if you calculate the average is 1. So spin average is 1. So that means this is also called magnetism. So the spin average is 1. So the material is magnetic. So this setup creates it's like a huge magnet. Okay, so what happens if you heat it up a little bit? Okay, so these little particles here around the spins they represent the heat, or the particles, ambient particles. They will hit these spins and they will try to randomize them, not try to flip them in a certain direction, but they will just try to randomize them. But even if you're still below TC, critical temperature, then still, okay, some of the spins are maybe flipped, but overall the magnetism will be preserved. It's not going to be 1, but it's going to be close to 1. So the system is magnetic below TC. So that's what I say here. Material becomes magnetic below TC. So the average spin below TC is non-zero. But if you heat the system a little bit more, then a phase transition happens. So when you go above TC, now all the spins are randomized. And if you want to calculate the average spin, which gives you the magnetism, and you would get actually 0. So here these two phases, so these two configurations, they correspond to a magnetic phase. But this one above TC, this one is non-magnetic. So this is a phase transition happening here. Okay, so as I said before, spins want to align to minimize the average energy. Okay, so let's say if you have this particular configuration, how do you calculate the total energy? So you have to count all the spin pairs. Okay, so this negative energy is in the formula here. So let's count the energy of the spin pairs. So these are in opposite directions. So let's say this is going to be plus, this is negative, this is negative, this is plus. So when you multiply them, it's a negative sign. So we get negative here. If you multiply them, there's negative here. If you multiply these two, -1, and this one is also -1. So the final result for the total energy is 4 for this particular configuration. Okay, what about the heat? So the ambient heat, so these little particles are representing the heat. They basically they want to randomize the spin directions, and this is quantified by the entropy term Ts. T is the temperature, S is the entropy. How do you calculate entropy? The Boltzmann entropy formula is this one. So the entropy is logarithm of multiplicity of the states. The idea here is by respecting this constraint that the total energy is 4, how many different configurations can you get? So one possibility is this one. So up, down, down, up. The other possibility is down, up, up, down. So these, if you calculate the energy for each of them, they are the same 4. You may ask, are there other possibilities like, let's say, up, up, down, down? No, I mean, this configuration, the energy, if you calculate the energy, it's not 4. So the only possibilities for 4 spins in this lattice is there are actually 2 ways, so the entropy will be log 2. So again, you don't just minimize the energy, you try to minimize the energy, also you try to maximize the entropy. So that's, by definition, that's free energy. You try to minimize the energy. By minimizing free energy, you try to minimize the energy, you try to maximize the entropy. So it becomes minimum when the thermal equilibrium is reached. So free energy is analogous to the objective function in machine learning, such as KL divergence. So if we are to make a connection between spin systems, Ising's spin model, and the neural networks, so I can say this, final spin positions. So let's say you have multiple spins, and they can, each of them can be up or down. So the final spin positions, when the free energy is minimized, correspond to weights learned in neural networks. So they can be up or down. In this case, so +1 or -1. So those would be the weights in the neural networks. Okay, we are not interested in the states of the spins at the individual level. Like, we are not really interested in what is the position of each spin, just like we are not interested in the particular weights in neural networks, right? So the observables are macroscopic variables, not the spins themselves, but the overall, the aggregate situation, the macroscopic variables, just like magnetization or the spin average that we calculated before. So, so the examples to macroscopic variables are magnetization, temperature, energy, etc. In the context of neural networks, the corresponding variables may be output layer as the weighted average of hidden layers. So in neural networks, you also do some kind of averaging. So the output layer can be seen as a weighted average. Okay, now the question is, how does magnetization or the average spin change with temperature? We saw that below TC, it was non-zero, but if you go above TC, a phase transition happens and magnetization goes to 0. So what is the quantity that encodes this, how magnetization changes with temperature? So if you're at thermal equilibrium, then it's the free energy. So basically, thermal equilibrium free energy is minimized. So what's shown in this plot is it's free energy versus magnetization. So these different curves, they represent different temperatures. This one, for example, is the highest temperature, 2.4, and the cyan color is the lowest temperature. And the phase transition happens around 2.2. So this curve is the one. So above this curve, this is like high temperature. This is like TC, and below the curves below the TC curve is the low temperature curves. Okay, you can see that F has minima at different positions depending on the temperature. So, for example, if you are at high temperature, let's say you are above TC, you are on this curve. Okay, so this is the free energy. So if you're at high temperature, then everything is randomized. So there's really no magnetization. And you can see that if you minimize this curve, the minimum occurs somewhere here, right? And what is so this is the free energy minimum. What is the magnetization that corresponds to this point? It is, as you can see that, at 0. So at this point, there's no magnetization. But if you cool the system down, and you can notice here that exactly at TC, a little dip starts to occur here and here. And after that point, the minimum of the free energy is never at 0, but at some non-zero value. So if you go to zero temperature, for example, well, in this example, it's not 0 temperature, it's actually 1.6, but it's way below the TC, so it's a low temperature. Let's say all the spins are aligned in the negative direction. So the minimum of the free energy at this low temperature occurs here, and that corresponds to the magnetism -1. So what this tells is basically there is the macroscopic magnetism produced is in this direction, in the negative direction. You may ask, what is this dip for? Well, that minimum is actually for the same thing, except all the spins are up. So that corresponds to the case where, again, low temperature, but in this case, all the spins are up. Okay, so now we learned that this randomized high temperature configurations, they correspond to, they have minimum at this point, and they have no magnetization. And for the cases where all the spins are down, then that corresponds to some non-zero magnetization. So let's try to interpret what's happening here. So this one, the top one, it's high temperature, and you can see that it's pretty randomized. At high temperature, if you remember, the ambient heat is trying to randomize the spin direction, so they cannot really, the spins cannot be really in the, even if they want, because of the energy term, in the same direction aligned, but the heat actually breaks that alignment. So this phase is disordered, it's random, and it's untrained in the sense of machine learning. So this is not the minimum of the loss function. So the magnetization is 0. Here the information is incompressible. The information is completely random. We cannot really compress it. There is complete ignorance here. If you think about the probabilities of each spin, they can be either up or down. So each probability is 1/2. Well, the probabilities are always plus. So up or down, they're 1/2. So there's complete ignorance. They can be anything, up or down. If you want to calculate the Shannon entropy or the information entropy, so the up case is, the probability is 1/2. For the down case, the probability is again 1/2. And if you calculate it, you find log 2. This is per spin. So for each spin, the entropy is log 2. Well, this is high because for this case, we're going to find 0. This is actually the maximum that can be for one spin. So it's a high entropy case, and that also means there's high information content. Okay, what about the low temperature? So all the spins, at least most of them, are aligned. Maybe there are some certain spins that are not aligned, but it's either -1 or almost -1. So that corresponds to the low temperature case. It's ordered, it's trained. So in the sense of machine learning, that's the minimum of the objective function. And there is this order parameter magnetization as -1. So the information here is compressible, because if everything is down, you know that all the spins are down. Then you can, you don't have to know each spin individually. You can say, okay, all the spins are down. So there's complete knowledge. You know that the down case, well, the probability, this is of course plus, for being down is plus, probability for being up is 0. And if you calculate the entropy for down, it's 1, for up it's 0, and if you calculate it, it's just 0. So that the entropy is 0 means we actually know everything about the system. So it's low entropy, and that also means low information content. Okay, let's move to the famous problem, traveling salesman problem. So here's a simulation. So the problem is there is a salesman that has to go to several cities in the country, and the question is, what is the minimum total distance that he can travel, but at the same time he can visit all the cities. So the loss function, or the objective function here, is the distance, the total distance. As you can see that it first starts with random path, and then it minimizes it. And there is this temperature here. You can see that. It's of course not real temperature in the thermodynamical sense, but it's just a parameter. So it goes down, and when it's minimum, the distance becomes minimum. You can also see it here. So this vertical axis is the distance, and the horizontal axis is the iterations. As the iterations proceed, so the distance after some number of iterations, the total distance traveled goes to minimum. So learning is cooling down in the sense, if we think about this temperature, it's cooling down. Again, it's not a real temperature in the physical sense, but it's just a parameter. But we can think of it as, it's the same idea as in the statistical mechanics. So as the temperature cools down, the system goes to the minimum energy state, or in this case, the minimum distance. So the system reaches the optimal state. Here, the temperature is decreased with the small steps of delta t to reach the minimum of the cost function. The cost function is the total tour distance here, this one. And the learning rate, it's basically the step size in the temperature. So delta t is the step size, and it's the learning rate in the context of machine learning. Of course, delta t may change as you move, so it can be adaptive. So as the simulation goes on, so you can also change delta t. And this is the connection between, again, statistical mechanics and optimization problems. Okay, so Ising model, as you saw, is not really interesting, because the free energy minimum, and the free energy is minimum, it corresponds to the case where all the spins up or all the spins down. So when you go to the 0 temperature, So one of the minima, if you remember the free energy, the minima, one of the minima is for all the spins up, the other one is all the spins down. The reason that happens is because all the interaction, all these bonds between the spins is taken to be the same in this model. So in this case, we took it to be 1. But it doesn't have to be. There are other models which model certain physical systems. They're called spin glass models. They're actually richer. So in spin glass models, the minimum energy states correspond to rich spin configuration. So if you go to the, if you minimize the free energy of a spin glass model, you don't find something like this, but you find a configuration where some of the spins are up and some of them are down. And this happens because the bonds now, or the interaction energies or the interaction strength between different spin pairs are different. So in this case, the interaction strength, it depends on the spin pair. So instead of 1, now we have Jij, and it can be positive, negative. Typically, it can be a number between -1 and 1, or it can be some Gaussian distribution. And the spin glass models are similar to, they resemble, if you ask me, the connection between the physical model that resembles like the neural networks. It's not the Ising model, but the spin glass model, because the minimum is it has not all the spins in the same direction, but some of them up and some of them down. And the analogy here is the spins are the final spins. When the system is in the minimum, when the free energy is minimized, the spins, they correspond to the weights in the trained neural networks. And if you ask me, what is the free energy versus magnetization plots for spin glass models? So this graph is for spin glasses. Remember, for Ising model, there was just 2 minima, 1 here and 1 here. But in spin glass models, there are actually multiple minima. And each of these correspond to different spin configurations. For example, this may be like this. The other may have some other configurations, but they all minimize the free energy. So this is another analogy between the spin glass models and the neural networks, because we know that neural networks, they have in the ground state or in the minimized, when the objective function is minimized, there are many possible minima. So in that sense, there is another analogy between the spin glass models and the neural networks. Okay, here's an interesting question. So why deep learning doesn't get stuck to a local minima during training? Why does it find the minimum so effectively? If we think about the number of parameters today in neural networks, the modern trained neural networks, they have billions of parameters, okay? The question is, even though there are billions of parameters, how is it possible that it finds, well, billions of parameters means there are actually so many minima, and they can be local minima. The question is, why is training so effective so that it doesn't get stuck in local minima? So what I have here is a 3-dimensional loss function, loss landscape. Okay, so in 2 dimensions, sometimes, you know, it's, if you think about this, let's start with 1-dimensional maybe. In 1 dimension, it's possible that during the minimization training process, the training gets stuck at some local minima instead of this global minima. But if you think about 3 dimensions, this is 1D. We can also think about 2D, but let's go to 3D. the answer actually, if we zoom in, so let's say the minimum point is somewhere here. Let's say you start training from here, and then you go down. It looks like at this point, it looks like you are stuck at a local minimum, but this is not really a well. This is a saddle. So you can actually continue if you do, let's say, stochastic gradient descent or similar algorithm. You can actually, you don't get stuck here because this is not a well, this is a saddle, so you can go down and find the real minima. So that's the nice part of the high dimensional lost landscapes. You don't get stuck because they're not really wells, there are either saddles or flat directions. So there are billions of weight parameters in DNNs, deep neural networks. So flat directions and saddles are abundant in thousands or billions dimensional lost landscape of deep neural networks. So it looks like it's a bad thing to have multiple minima, but it turns out because of the high dimensional lost landscape, it's actually a good thing because you have a lot of flat directions and saddles so that the training becomes really, really effective. Okay, so let's move to restricted Boltzmann machines. But before that, let me talk about probability, the concept of probability in statistical mechanics. So let's say the question is, let's say at a given temperature, how probable is this configuration, or how probable is this configuration at a given temperature? So how do you quantify this? Well, probability of a specific configuration at temperature T is given by the Boltzmann distribution. So it's this formula. So basically, the probability of a particular configuration, which it could be this one, for example, is exponential negative energy of this configuration. You have to calculate the energy of the total energy by multiplying each pairs, okay, plus or minus, and then divided by temperature. And there is in the denominator, there's this normalization term, so it's just a number. So the probability of any state or configuration is actually related to, it's proportional to the exponential of that, the energy of the state. And again, you can calculate the energy of a given configuration, for example, this one, by multiplying the spin directions, either positive or negative. So this configuration is more likely at low temperature because it's magnetized. Like there's really tiny amount of randomization, but it's almost like ordered. And this configuration is more likely at high temperature. And how do you know them? You can actually calculate them from this Boltzmann distribution. Okay, so, but the question is, why do we have such exponential function? Well, that Boltzmann distribution, it comes from maximization of Gibbs entropy. So you want to maximize the entropy. So this is the statistical mechanics part. So you want to maximize the total entropy, and also you have to add the fact that all the summation of the probabilities should add up to 1, and you have to also consider that there is this constraint of energy conservation, or if you take the average energy, it will be defined, so it will be equal to some average energy variable. So basically, this Gibbs entropy, the probability condition, and the energy definition, it gives you all of these. If you maximize these, they would give you the Boltzmann distribution. This is important because we are going to see that the machine learning models on restricted Boltzmann machines, they will have the same probability, and well, actually there are That's the reason why they're called Boltzmann machines. And the reason that they are, the fundamental reason is that they are using they're minimizing certain entropy function, and also there is this energy defined. So they're called energy models. Okay. So restricted Boltzmann machine is a generative neural network architecture. They're similar to the spin glass model because in two senses. One of them is the restricted Boltzmann machines accept only binary inputs. So there's this, so this is the architecture. There's this visible nodes. So they're the inputs. And there's this hidden node. There's no output. It's just this. So the inputs, the model accepts only +1 and -1, or spin up or spin down. Okay, so in this sense, they are like the spin glass models. But the weights can be anything. So these weights can be anything. The second analogy is between the RBMs and the spin systems is that RBMs are energy-based. So because they're energy-based formulations, Boltzmann distribution between the visible and the hidden nodes arises naturally. So if you write the energy, in this case, for this architecture, it is some function of the nodes. So I'm going to use S. So we can, for the visible layer, we can use VI. For the hidden layer, we can use H, let's say J. So there is this definition of energy in this model, and you try to minimize it, also try to maximize the entropy, and that's why you end up with Boltzmann distribution in this model. So how this works is let's say you rate some of the movies. Let's say you say, I like Lord of the Rings, I don't like Matrix, I don't like Fight Club. I like Harry Potter, Titanic, not liked, The Hobbit, not liked. So given these inputs, this model tries to infer that given these inputs, if this person, whoever, so the person that made these choices, if the probability distribution is trying to guess if that person likes fantasy movies, for example, or science fiction movies. So for this particular selection, it turns out that the highest probability is that person likes fantasy, not drama, and not science fiction. Okay, let's move to autoencoders. Autoencoders are they are unsupervised learning methods. So they're useful particularly for finding latent means hidden variables in the data. So what you do is typically train this. This is unsupervised. There's no label, so you use for training data. So whatever you use for inputs, you also use for outputs, the same data. So the question here we can ask, let's say, can the code layer, so this middle layer, encode thermodynamic variables like magnetization? The idea in this architecture is that so certain amount of information enters here, but because there is this bottleneck, this architecture autoencoders, they have to compress the information at this point so that they can, the information can continue flowing. So the question is, can this compressed information can it correspond to certain latent variables in the system? So it turns out if you use this for spin models, Ising spin model, turns out that there is the latent parameter and magnetization they are linearly correlated. You can see it here. So So as the magnetization changes, latent parameter changes linearly. So that means basically latent parameter is demagnetization. So the nice thing here is this is an unsupervised architecture method, and so the autoencoder learns this magnetization by itself. So that's the nice part of it. And if you plot this magnetization and the latent parameter respect to temperature, they're actually on top of each other. And you can even distinguish the two phases. The magnetic phase here, you can see that the magnetization is almost 1 here. Here, the magnetization is almost 0. So this is the magnetic part. This is the magnetic part. And this part is the non-magnetic. Okay. Now you can look at the border that distinguishes these two. It's around it's around 2.2 or 2.3, and it's indeed the critical temperature in the model. So this unsupervised model can actually distinguish the two phases and learn from the data what's important in the data, in this case, the magnetization. So let's move to convolutional nets in the physics concept renormalization group. So the convolution neural nets, they are used for images, to classify images. They used, first, there is this convolution layer. So it basically calculates the convolution of certain filters and the original image. And then there is some activation function. And after that, there is this pooling layer. So what I'm interested here is the pooling. So what is pooling? Let me show you on this example. Let's say this is the image and the pixels and the pixel values. Let's say what pooling does is, let's take this part. So it's kind of an averaging. Let's take these 4. If you're doing max pooling, it's taking the maximum value, which is 30, which is here. If you do average pooling, 30 plus 2 is 32, divided by 4, it's 8. So you can do average pooling, max pooling, whichever you want. There are other methods as well. But it is some sort of coarse graining, or you can say zooming out, or you can say downsampling, or in a physics language, integrating out fine details and leaving out the large scale structure. So it is kind of like zooming out from the picture. So, okay, how do we use it in physics? Well, in physics, this idea is used, and it's called renormalization group. It's mainly used to discover the scaling laws, or scaling laws are power laws, that quantities like specific heat, correlation length, and magnetic susceptibility obey. So you may ask the question, how specific heat or other thermodynamic variables, how fast they grow or go down as you approach or go away from TC, the critical temperature. So how does it work in physics? Let's again go with the Ising spin model. So what you do is you take, you can take 4 spins here, for example. Okay, and then you can either take the average, or you can take, for example, in this case, you can say there are 3 up, 1 down, and you can use the majority rule because there are 3 ups. You can say this could be 3. Let's use the majority rule. For this one, this block, the majority is down, so you would say it's going to be down. For this block, the majority is again down. Here we have down. For this block, the majority is up, so it's going to be up. So you can continue like this, and then you can do it again for this block here. The majority is down, so it's going to be down, and you can continue like this. So you basically, so this is the original spin system, and you reduce it to a spin system where there are only 4 spins, and you can even take the average here as well. So you are zooming out from the system. So the question here is how the free energy changes. So now we don't ask how free energy changes with temperature, but we ask how free energy changes as I do this pooling or averaging or using the majority rule. Remember, free energy is our objective function in statistical mechanics that we want to minimize. Okay, how the free energy changes with pooling or averaging spins tells us how thermodynamic variables change at temperatures close to the critical temperature. So in physics, we use this to get an idea about the exponents of the functions like specific heat, correlation length, and other thermodynamical variables. This is an interesting subject. It's in physics, this is applied almost any field. You can find a renormalization group in condensed matter systems, in high energy like quantum field theory. So it's used in almost all fields of theoretical physics. You can read on this if you want. If you're interested, you can read the paper from Mehta and Schwab, or you can read one of the papers from Lin, Tegmark, and Rolnick. Okay, now the references. There are really nice books on this one. This one is from late McKay, Information Theory, Inference, and Learning Algorithms. This is really nice book. There's a lot of physics in this book, especially about Ising systems, phase transitions, and whatnot. And there is another book which is pretty good, Statistical Mechanics of Learning. You can check that out too. There are certain reviews and surveys. The first one is, it's published in Reviews of Modern Physics. There are other ones that are really useful. You can, if you're interested, you can read them. And there are many more. So I did not include here, but you can find, if you go to references of these reviews, you can find those papers as well. So finally, let's collaborate. Physics-inspired AI is new and exciting field, so we invite you to continue this journey with us. Let's figure things out together. Extensive set of resources, related work, surveys, current projects, and call for papers are maintained on our Physics-Inspired AI project website, so you can check that out. And please feel free to contact either Mohammed or me. And thank you very much for listening.